Welcome to a walkthrough video for the higher worksheet for the unit 2.2, which is acids, bases, and salts. Question 1 is a simple equation about preparing an insoluble salt. So the first task is to determine what A is. So looking at the equation, we've got a carbonate, calcium carbonate on this side, and calcium nitrate. We need to account for this carbonate on the product side, so we must include it on the reactant side. So we need any soluble carbonate salt, and a couple of examples could be sodium or potassium carbonate. So then we need to name compound B. So as we said, we've got a carbonate, we've got a nitrate, we're going to have a carbonate here. We know that this is a carbonate now, so we're going to have another nitrate here. So any soluble nitrate, but to get the full marks for this question, you must relate it to the previous answer. So for example, you've used sodium carbonate here. You're going to have sodium nitrate here, but if you use potassium carbonate, you're going to have potassium nitrate. So that's part one of the question. So the second part of the question is a student carried out the reaction and observed the formation of a white solid. So what do you think this white solid could be? So we know what our equation is now. We've got calcium carbonate and we've got a nitrate. And if you remember, you'll know that calcium carbonate is actually a solid and it precipitates out. So this is going to be the calcium carbonate, and then you would want to isolate this solid. So to isolate a solid, we typically would have to filter it out. So we've either got the typical setup you might have used at secondary school, and you would have used some point at A level, just gravity filtration. But you can also do vacuum filtration, which instead of letting gravity pull the liquid through, you suck the liquid through with a vacuum and separate it out this way. So the last section is how could a soluble salt be separated from solution? So up until this point, we're filtering out insoluble salts. But if we've got a product that's actually soluble in water, we're going to have to use a different approach. And for this, we would evaporate the solvent, so evaporate off the water and everything to leave behind the salt. And we could also use a Bunsen burner and an evaporating dish. And this is what that equipment would look like. Question 2 is about a bunch of different reactions that involve nitric acid. So as a quick refresher first, what would an acid and metal give you if you reacted them? So take a second and just think about it. And if you were thinking salt and hydrogen, you were right. Same again for an acid and base, what would that give you? If you said salt and water, you'd be right. And the final one we're going to look at is carbonate plus acid. So think about what that give you. And if you said salt, carbon dioxide, and water, you'd be right. So, part A of the question, we want to name C, B, and E. Naming C, we've got C, B, and D as all unknowns in here, which is going to be quite difficult. So if we go to the one above it, we've got an acid, nitric acid. It says in the question, don't ignore information like that, because that could be really critical to know that this is called nitric acid, and you'll see in a second. So copper oxide, so we've got a base. The copper oxide is a base, we've got nitric acid, and we've got blue solution B plus water. So blue solution B is going to be a salt, and it's going to be copper, as it's our only metal. And we've got the nitric acid, so it's going to be copper nitrate, which is why I say it's good to look at information like this in the question, because if you know that this is nitric acid, getting copper nitrate as your answer is going to be a lot easier. So we can move on to this one down here. So we know that blue solution B is a copper nitrate solution, but instead of just having water here, we've actually got a gas as well as a product. So this powder cannot be copper oxide because it gives a different product. So we've got a gas, which I guess that could either be hydrogen or carbon dioxide or anything. But just by looking at these equations, the only ones that's got three products, we've got salt, carbon dioxide, and water. So this is going to be carbon dioxide, which means that this powder is going to have to be copper carbonate because it's a carbonate plus acid. So moving on to E, we've got an acid plus something, giving us sodium nitrate and water. So sodium nitrate, this is just a type of salt, but instead of written out as its chemical formula like magnesium nitrate up here, it's just been written down. So to know that this means NaNO3 like this is very useful. So actually answering the question, we've got an acid plus something to give us salt and water. So it's going to be a base. And what bases do we know that have sodium in them? Quite common one, sodium hydroxide. So that's the first part. So now naming the gases is a lot easier. So naming A up here, we've got acid, metal, salt plus A. So acid, metal, salt plus hydrogen. And then down here, we've already discussed that it's going to be carbon dioxide. So with these gases, we actually need to test for them as well, because you might do a reaction and you've made this and you've made this, but you have no way to tell because they're both gases. So hydrogen, you can identify it with a pop test. So you use a light splint into the test tube and you'll hear a little pop if you have hydrogen. And then if you want to see if you have CO2, you bubble it through lime water and it'll go from this clear color to a milky sort of color. And that's how you know you've got carbon dioxide. The next question, question 3, is a simple titration question. So the first question says, what would the chemical equation be for a reaction between hydrochloric acid and sodium hydroxide, including state symbols? So first things first, we need to, what we talked about in the last slide, we've got an acid plus a base giving us salt and water. So we've got an acid plus a base giving us salt and water. So here we've got sodium and we've got hydrochloric acid, so we've got sodium chloride. That's how you can name this. So we've got the water and the sodium chloride here. So you also might be wondering what the state symbols means. So we've got AQ here, which stands for aqueous, and Al here, which stands for liquid. So Al just means that this is water, it's pure liquid, and the AQ means it is aqueous and dissolved in water. And then obviously if you've got a gas or a solid, you put a G or an S there instead. So the second part of the question is determine the average titer of this reaction, accounting for any anomalies. So we've got our total HCl is 45, of these all added up. So this isn't including the rough one, because the rough one is a rough titration, and this one here is too far away. So adding these two up together, we get 45. So our average titer is going to be over 2. So divided by 2 because we've got 2 there, and we've got 22.5. So from this value, we need to determine the concentration of the sodium hydroxide. So in the bottom of this beaker, we've got sodium hydroxide that we do not know the concentration of. And up here, we have a 0.2 molar hydrochloric acid. So we need to use this equation. We've got moles equals concentration times volume. And if we plug our numbers in and we work out the moles of HCl added. So the first thing we do in this question is work out how much of the stuff in the burette we have added, because we know the concentration. So we've got 0.2 molar, and our average titer goes in here. And we divide by 1,000 to put it into decimeters cubes, into decimeter cubed. Let me just write that down. So that converts centimeter cubed into decimeter cubed, which is what you need to answer the question. So we work out the moles of HCl, and this is 0.0045 moles. And then we can work backwards. So we know that we have 0.05 moles of HCl, which means we must also have 0.05 moles of sodium hydroxide. Because if we look at this, this part of the equation, we've got HCl plus NaOH, we've got a 1-to-1 ratio, which means for every mole of HCl, we're going to have exactly the same, for each part of acid, we're going to have an equal amount of the base in this situation. So working out the concentration of NaOH, instead of working out the moles, we need to work backwards, because now we know the moles and the volume. So the volume is 25, and we can see this pink arrow pointing to it, 25 there. And again, divided by 1,000 to convert into decimeter cubed. And we've got a 0.5 moles, as it's the same as the hydrochloric acid. And then you just plug this into your calculator, write it down, whatever, and you'll get this answer at the end. So the way to work through these questions is to look at what you have. And the first things you have are a couple of volumes, and you can work out some moles, and from there you'll be able to work through the question quite well. Question 4, part A is about iron chloride, and the question wants you to write a balanced equation for the reaction between iron chloride and sodium hydroxide. So we start off with our reactants. We've got iron 3 chloride and sodium hydroxide. And then these are going to make sodium chloride and iron hydroxide. So like this. But balancing this equation is maybe not so straightforward to begin with. But it's not actually that hard. So we've got one iron here, and we've got an iron here, so we can cross those out. But we've got 3 chlorines here, but only 1 here. So we can put a 3 in front of that one. But now we've got 3 sodiums, so the chlorines are cancelled out at this point. But we've only got 3 sodiums here, but only 1 here. So if we put a 3 there, the sodiums cancel out. And we've got 3 oxygen, because this is 1 oxygen in the bracket times 3. And we've now got a big 3 here. So we've got 3 of these, and we've got 3 hydrogens, which will cancel out that. So a good thing to maybe think about when you're balancing these as well is that chlorine is going to have a charge of -1. Iron 3, this 3 means it has a charge of 3+. So say you saw this on a paper with just the 2 lines. This is iron 2, and this is going to have a 2+ charge instead. Whereas chlorine is always going to have a -1 charge, and hydrogen is always going to have a +1 charge. So the next part of the question is about identifying solutions. So a student has potassium chloride, potassium iodide. They do not know which one is which. Can you think of anything that we need to add that would help us find out what is what? So what you would do is you would add silver nitrate, and if it turned yellow, it means it's the potassium iodide solution, and if it turned white, it's potassium chloride solution. There's not too much to remember here, other than you need to know the colors when you add this here. When you add silver nitrate, that's what this is. You need to know the colors of the precipitates. And one way of remembering it is iodide is yellow, so at the bottom, and then the chlorine at the top. Further up the periodic table is less yellow. But I don't know, you just need to remember those. The next question is about the reactivity of group 1 metals. So looking at the group 1 part of the periodic table first, we don't have cesium or francium in this question, so we'll ignore them. But as you go down the group, they increase in reactivity. There are lots of reasons for this, but for simpleness, lithium is less reactive than rubidium, and they increase going down. So going over to the question, we've got number A is a violent reaction with sparks. So we know that this is clearly more reactive than any of the other ones. So this is going to be rubidium for A. B is gentle fizzing. We're comparing it to C and D. We've got the metal ball, because it's dropping a ball of metal, one of these, into water. So it either fizzes and moves around the surface, or it melts and moves around. But this one doesn't do either. So this is going to be the least reactive. So B is lithium. And then comparing these ones, this one, C melts. This is the most important thing here. C melts, whereas D doesn't, which means C is going to be potassium and D is going to be sodium. And I've already kind of spoiled the answer for this one, but this is a walkthrough video, so hopefully you've already done it. Francium lies at the bottom of group 1, all the way over there. So predict what will happen when it reacts with water. So if these are getting more reactive, and we've got explosions as when we've got to rubidium, if we get to francium, it's going to be crazy. So just an answer like an even more violent reaction or something like that will do. But with reactions like this, you might want to take some safety precautions. So there are many different precautions here. You could use excess water, because obviously if you've got more water, the explosion is going to be the fizzing, the metal ball fizzing around is going to be less. A smaller amount of metal, same thing. A screen, fume hood to protect you, goggles, gloves, etc., etc. This is question 5 continued on, and part B is about metal oxide formation. So there's a nice hint in the question, sodium oxide. So sodium oxide's formula is Na2O, and it contains Na plus and O2 minus ions. So when you make a compound like this, the overall charge equals 0, and Na plus has an overall charge of +1, and O2 minus has a charge of -2. So to have this balance out to have 0, you're going to need 1 oxygen and 2 sodiums, hence how you get Na2O. So actually circling them, we got this one, we know is right. We know that this one can't be right, the second one, as this would give -4, and this is +1, and that doesn't cancel out. The same here, we've got +1 and -2, whereas here, this is maybe a little bit of a tricky one, as this 2 at the front sort of means like in a bracket, so two lots of NaO. So again, this is +1, and this is -2. It can't work. The same down here, same as above, but this one we've got +2. We got -2. This one we got +2. We got -2. What about this one? Have a quick think about the last one. Well, we can't, because it's almost like you have a bracket there and a 2 on the outside, and this is +1. This is -2. So the only other two that are going to be right, have a quick think, have a quick guess. No, well, not a guess. Hopefully you know what the answers are, but it's going to be these two at the bottom, because we've got +2, -2. They cancel out to 0. So just as a little explanation, but this isn't too important. You just need to, when you make these formulas, make sure the charges balance out and are 0. But as you can see here, we got -2 for the oxygen, and we got 2 of the say the sodium ions or the potassium or the rubidium. So the final part of question 5 is group 1 metals also react with chlorine, producing metal chlorides. Write a balanced equation for the formation of potassium chloride and using Cl2. So this is really important. You need to use Cl2. So we've got, so what you would write by yourself is you would write potassium plus Cl2, just to start off the question. And you know the equation for potassium chloride is KCl. Because as we've been going through this entire one, we know that K plus is +1, and we know that Cl minus is -1. So to balance each other out, it's just 1 to 1. But this says use Cl2 in your answer. So to balance this equation, we've only got 1 chlorine on this side, so we're going to have to put 2 there. And now the chlorines balance out. But we've got 2 potassiums here and 1 potassium here, so we're going to have to put 2 there. And then you can see we've got this equation at the bottom. That's quite a nice simple question. It doesn't say anything about state symbols or anything here. So this is just quite an easy 2 marks because it tells you what to use in your equation. But the only thing you shouldn't get caught out by is balanced equations, because you could potentially have this, a half Cl, but that wouldn't answer the question right, as it says use Cl2 in your equation. Question 6 is about the preparation of different salts. So before we actually do anything, we're going to refresh ourselves about some key equations. So the question says lab tech needs 0.01 moles. So we're going to use an equation with moles in it, and we know moles equals mass over molar mass. And then the question goes on to say what mass is needed for the experiment. So we want to rearrange this to give us the mass. So we've got mass equals moles over molar mass, and we know that the moles we want is 0.1, and then the molar mass of each compound is just worked out here. So this is quite a simple question. I'll walk you through working out the mass of this one. So we've got Na. The mass at Na is 23. The mass of chlorine is 35.5. Add them together, 58.5. And then the same here, except you've got 3 calciums. So this one has 3 calciums in it, because you've got Ca3, and you've got 1 potassium, but a 2 out here, which means you've got 2 potassium. And you've got 4 oxygens, but a 2 out here, so you times that by 2. Which means you have 8 oxygens, and then altogether this will add up to 310. This one down here is a bit more simple. So using this equation, we've got our molar mass, 58.5, times the moles, 0.1, gives us 5.85 grams. And then we just follow the same method for the other two. And these are our answers. So quite a simple first question. The next question is about preparing a sodium chloride solution. So complete and balance the equation below. This is what we've been doing the entire time. So on this side, we've got H2 from this equation, but we also know that we have sodium chloride. And on this side, we've got this. So if you think back, what equation gives you a salt and hydrogen? Metal plus an acid. Metal plus acid gives salt and hydrogen. Let me just remove some of these. So that's quite easy. For the first step. So now we just need to balance it. So we know our metal is going to be the sodium. So we've got Na plus HCl gives NaCl plus H2. We've got 2 hydrogens on this side, but only 1 on this side, so we put 2 there. We've now got 2 chlorines, so we've only got 1 chlorine, we'll put 2 there. We've got 2 sodiums, only 1, put 2 there, and then you can see our equation is nicely balanced out. So the final bit of question 6, the student was given solid sodium chloride from the lab tech to make up their solution. Using your answer from A, calculate the percentage mass of sodium in NaCl. So this question's a little bit different from what you might have seen before. So this is just a bit of maths. We want to work out what percentage of sodium chloride is sodium. So we've got the molecular mass of sodium, 23, chlorine, 35.5. And it's just a simple percentage calculation. So the mass of the sodium here, over the entire mass of the compound, which is, I'll just call it salt because it is just normal table salt. So we end up with 23 over 23 plus 35.5. It gives us 0.393 times by 100, 39.3%. That's how much of sodium chloride is made up of sodium. The next question is quite similar to a lot of the previous questions we've already seen. So what would the products be if a carbonate was reacted with an acid? So we've done this quite a lot, so I'm not going to spend too much time on it. Carbonate plus acid. Just take a second and write down the answer. Salt, carbon dioxide, and water. Quite simple. So a student mixed some magnesium carbonate with dilute hydrochloric acid and saw bubbles during the reaction. Write down a balanced chemical equation with state symbols for this reaction. So we know that we've got the magnesium carbonate, which, that's kind of bad drawing, is going to be a solid, plus hydrochloric acid, which is aqueous, AAQ. And then we've got our water, which is a liquid. We've got our CO2, which is gas. And when we know that these two are products from up here, these two. And then we've got a salt, which is going to be magnesium from here, and then the chloride from here. So Mg2 plus. And then what's the charge of chlorine? Just have a quick think for a second. We talked about it earlier, but if you said -1, you'd be right. So to balance this out, we're going to have 1 lot of this for 2 lots of this. That is a 2. So we got MgCl2. And then with the state symbols, we got aqueous, gas, liquid. Don't forget them. But quite a simple one. As long as you know this equation at the top, the one that I've just highlighted in purple, because it's really important. As long as you know that, you can answer any of the questions in B. So, if a student, part B, II. If a student didn't know what gas was produced during this reaction, how would they identify the gas? So, obviously answering this question, you should know that the gas is carbon dioxide. As I said, from the most important, from the thing I've highlighted at the top. So we know it's carbon dioxide, and we know that if we want to identify carbon dioxide, all we do is put it through lime water, and it'll get cloudy. Simple. Pretty easy, pretty easy. Question 8 is about how much carbon dioxide is produced in a reaction between an acid and a carbonate. So between dilute hydrochloric acid and magnesium carbonate. So the first bit of the question is A, down here. So fill in the table for the amount of gas produced at 15 minutes. So this is the little picture of what it was, and we can see that it's going to be 61 and then 62. Let's put 62 in there. And you always read from the bottom of the meniscus. We've also plotted all the points from this. I did it on this, so it's a drawn line, so it's pretty rubbish. But you can get the idea that it goes up and up and up, and then at a certain point it plateaus. So you can see that they're going to be 90, 90, and 90 at a certain point, because that all of the magnesium carbonate has reacted at this point, and you can't make any more carbon dioxide. So when you're drawing this graph yourself, this bit I've highlighted, you need to make sure this line is perfectly straight, because it can't go down, because you can't make 90 centimeter cubes of carbon dioxide and then go down to, say, 89. This line must be straight for the entire time. So part 2 of question 8. So on the same graph paper, sketch a graph for the results you'd expect if powdered potassium carbonate was instead used. So the curve would be to the left the existing one, and it would also stop at 90. But why would it do that? So this is answered in part 3 of the question. So there are more particles. So potassium is a +1 ion, magnesium is a +2. So for every one magnesium, there'd be 2 potassiums. But there's still the same amount of CO2, the same amount of the carbonate ion. So it's also going to stop at 90 centimeters cubed. But this just means there's going to be a greater chance of collision between particles, a faster rate of reaction. It stops at the same level. So let me just put a note that you can't make any more. Can't make any more. There's a set amount of carbonate in the system, but with potassium you just have more particles, so it's quicker. This next question is about ammonia. So the first question wants you to complete this equation and name the acid to make ammonium nitrate. So we've got ammonia here, we've got an acid here. This acid has nitrogen in it, so it's going to be nitric acid. And for this sort of question, there's a fourth equation you should remember. We've got ammonia plus acid gives an ammonium salt, which you can see down here. We've got the ammonia plus HNO3 gives this ammonium salt. So another type of ammonium salt is ammonium sulfate. And what acid is used to prepare this? Well, if this has got nitrogen in it and it's nitric acid, this has got sulfur in it, it's going to be sulfuric acid. So the next thing they did with the ammonium sulfate is they put it in sodium hydroxide and warmed it up, and a gas was formed. And someone took some damp red litmus paper and tested it. If they tested it, what would they see? They would see that the litmus paper would turn blue because of the alkaline gas that is being given off, the ammonium gas that has been given off during this reaction. And we can see just a little picture of what happens when you put either red litmus paper in a base, or in this case, we've got blue litmus paper. Oh no, we got the red. Sorry, I've got quite confused myself for a minute. But we've got the red litmus paper turning blue in the base, which is exactly what it would happen in this reaction. And this is what you would see. So the gas formed is ammonia. It's the alkaline gas. And then the last bit of the question is how would nitrogenous fertilizers enter streams and rivers? So anything to do with runoff from fields or farmland, anything to do with fertilizer spraying, and you'd probably get a mark on that question. This question concerns 3 different acids and 3 different metals. So for the acids, we've got 2 that we're familiar with throughout this entire PowerPoint and throughout the question papers so far. These are both strong acids. These are both strong acids. So what this means is when they get put into water, so for example, HNO3, place it in some water, it will break up into H+, and then the nitrate ion entirely. Whereas this one won't, and we'll see why in a second. So the acid that reacts slowest with iron is going to be CH3CoO, or ethanoic acid. Let me just write that down. Ethanoic acid. So why does this happen? It's because it is a weak acid, whereas, as we've said, the other two are strong acids. So what does this mean? This means that when you put this in water, CH3CoO, or ethanoic acid, is what I'll call it from now, you get the H+, which is present in all acids, but you also get CH3CoO-. So it doesn't entirely break down. When you put this in water, you're going to have a bit of this, a bit of this, and a bit of this. You have all three. Whereas when you place nitric acid in water, you only have these two ions. So basically, with the nitric acid, there's way more hydrogen ions about to react. So going on to the next bit, all these metals react with sulfuric acid, all of them, and place them in order of fastest to slowest. So the way you do this is look at the reactivity series on the side and highlight the ones you have. We have potassium, we have iron, and we have copper. So looking at this, potassium is the most reactive, copper is the least. So potassium will react quickest, copper slowest, and iron somewhere in the middle. So part B is writing down a chemical equation using the ethanoic acid. So a student reacted potassium hydroxide with ethanoic acid. So potassium hydroxide is KOH plus the CH3CoO. That is a H on the end, by the way. And what will this give us? This will give us, let me do the animations. We've got base plus acid is a water and salt. So base plus acid, we got water. So that is going to be, and it's going to leave us with K, CH3CoO. So depending on how you want to write it, it's either going to look something like what I've just written there. Let me get rid of all these drawings. Or it'll look something like that. So essentially, you've replaced one of the hydrogen ions with this potassium. You can sort of think of it like that, if that will help. So the final bit of the question, probably the easiest bit of this entire thing, is acids and alkalis both produce ions in solution. What ions are they? So as we know from this slide, ions from acid is going to be H+ ions, and ions from alkalis are going to be OH ones. So a quick example for that, we've got NaOH is a common alkali. When you put it in water, it'll give you Na plus OH minus there. So the final bit, acid and alkali undergo neutralization reactions when mixed. Using the species from the first part of the question, write down an equation for this. So these two are going to have H+ plus OH minus to give you water. So something acidic here, something basic here to give neutral water there. And then it's just the same equation underneath. So that's all the questions that we've walked through. But just as a final slide, something you should remember, we've got the key equations that you cannot forget. You cannot forget those. Another thing to point out is the naming of the salts. So in this little box here, if you use sulfuric acid, it's going to be a sulfate. Nitric acid is going to be a nitrate. Hydrochloric acid is going to be a chloride. And then we've got these two tests down here that are again very, very important. Make sure you know these tests. And then reactivity series and then litmus paper. Good luck. I hope you do very well.